once again to another great video. So now what we'll be doing on this one is a past control test paper from Limpopo in March 2024, right? So it was question 4 in this case, and then if we take a look at what we're given here, right? So we have a system of 2 blocks. They are connected by a light inextensible string. Well, the reason it's important to mention that it's inextensible, you will later understand that it's so that we can just assume that if object or if block 1 is moving at certain velocity, it means block 2 is also moving at that velocity. That can only be achieved if the string is inextensible, right? But that's not important for now. So what happens is now you have this system, and then we are told, remember when you are reading these statements, you underline the keywords or the given information, right? In this case, the 8 kilograms, the forces and so on, you don't need to underline that, it's already in the diagram. But rough horizontal surface, that tells you we have friction here. And then a force of 62 newtons is being applied to the 10 kilogram block. I'm not sure why these papers have typos, because this is saying 10, but we have 8 kilograms here. Nonetheless, it's fine. We'll use 8 kilograms because initially it was 8 anyway. So we'll stick to 8 for when we're solving. Now, and then this force that is being applied on the 8 kilogram block is at an angle of 25 degrees. What that means is this force will definitely have its x and y components. So from here, what will happen is you will get Fy, right, which is the y component of this 62 Newton force. I usually like to limit it to just here. So you'll have Fy going all the way until up there, and then you'll have Fx. And then you will have Fx. I usually limit it as well to here, going all the way there. Right, this is your, okay, it looks ugly. That's your Fx. So the x component of this 62 Newton force and the y component of this 62 Newton force. Okay, so we haven't even started solving for the problem, but we're just taking out whatever we are given. Right, the system then accelerates at this 3 meters per second squared, and then to the right, so it's moving this way, right? And then we are told that the acceleration a is 3 meters per square second. So now we are told that this 2 kilogram block experiences a constant frictional force of 2.1 newtons. Right, so if it's moving, it's obviously going to be Fk and not Fs. Fs is for static friction, Fk is for kinetic friction, remember that. And then we only are concerned with static friction if the system or the object is not moving. Once it starts moving, we forget about Fs, which is our static friction. We start considering Fk, right? So that's why I just wrote Fk here. So this is all the given information that we can currently use. And then let me just, right, this is all the given information that we can use. Okay, so now we go to 4.1. State Newton's second law of motion in words. And then this one, I always say, is very, very important. Before an exam or before a test, you go through your exam guidelines or the definitions that were given to you by your teacher for the chapter, depending on the scope that you have, and then you memorize them, because they you just need to make sure that you write that definition as it is. Of course, there's a level of understanding you must have when it comes to that definition. But if you want to get all these free marks, you make sure that you memorize all your definitions before you go and write. Because it's a free, in a final exam, it's around 13% of the entire exam. So that's a free 13% if you think about it. So when it comes to Newton's second law, usually we say whenever we have a net force being applied to an object of mass m, the object will then accelerate in the direction of this net force, right? It will accelerate with an acceleration that is directly proportional to this net force, but is inversely proportional to the mass of this object. Okay, so that's all you have to say for Newton's second law. So just like that. And then now, obviously it looks like it's a bit long, but it's not, I promise. It's just the way my page looks. It's definitely not wrong. I mean, not long, and it's actually easier to memorize. Right, you can even use the formula to remember it. The formula is F net is equals to MA. So all of this statement is actually in the formula F net is equals to MA. Directly proportional to the net force, but inversely proportional to the mass. How do you know it's inversely proportional to the mass? If we make the acceleration subject of the formula, you get something like this. So you see, it's inversely proportional to the mass. So it means if we increase the mass, the acceleration decreases, and vice versa. So now that's what we have. So the usually keywords here in this definition, you don't just mention it anyhow. Net force being applied to an object, and then you have object accelerates in the direction of the net force. That's a key phrase, it must always be there. And then the acceleration is directly proportional to the net force, but inversely proportional to the mass of the object. All those are key phrases. They must be there in your definition or when you're stating Newton's second law of motion. Now, we are asked to find to draw the free body diagram of all the forces acting on the 8 kilogram block. Right, let's bring it to that. So see here, we have 5 marks. It means we will have 5 forces in our FBD or our free body diagram. Okay, so that's 4.2. Let's go to 4.2. And usually before you even go to drawing the free body diagram, you can annotate it from the given statement or problem. So in here, we know that, let me erase this, we will have a normal force, then we will have mass, weight, sorry. And then due to this string or the presence of this string, we will have tension there. And then since this block is moving that way, right, and then it's on a rough horizontal surface, we will also have friction, Fk, right, going to the opposite direction. Now let's count our forces. We have 1, 2, 3, 4, and 5. So you know that if you draw all these forces on your free body diagram, you will get your full 5 marks. Okay, so let's do it. We just draw a dots first. So it'll be a big dot here because I saw there's quite a number of forces. We're just trying to make sure they all fit in this dot. And then we start with the given force, the 62 Newton force. Okay, my free body diagram looks big. (62 newtons). Then we have the weight. Some people call it Fg. It's up to you or your teacher or your school, whichever one you prefer, right? And then this angle, you don't have to put it here. It's fine. You can leave it like this. You don't have to put it there. And then you have the normal force. N. Some people decide to call it Fn. It's up to you, or it's up to how you were taught in school. And then you have tension due to the presence of the string. And then you also have your friction. I'll just make it smaller than the tension. We don't know if it's smaller than the tension though. So we don't know yet. So this is the free body diagram. So here you get your all 5 marks because you have all of your forces. And remember, you don't have to write these O's. Do not actually include these O's. It's just for me showing you that there are other people that write it that way. So you write it like this. No O's. Don't write O what. No. That was for me just showing you that there are other people that write it in a different way. In case at your school you write it like that, just know that you're still fine. Now we go to 4.3.1. Okay, this was 4.2. Okay, so now 4.3.1. We're asked to find the tension or calculate the tension in the string connecting these two blocks. So with this one, if you are in an exam and you're trying to calculate a question like, solve for a question like this. So what you want to do here is, if you check, tension is being shared by both blocks, which means if you were to draw the free body diagram of each block individually, you will find that T is present in both free body diagrams. So let me show you, right? The free body diagram for the 2 kg block, for instance, because we've already drawn the one for the 8 kg block, which is this one. For the 2 kg block, you would have something like this. Right, so you'd have something like this. So we are looking for tension, this guy. Okay, so we know that if we're looking for tension, we'd have to consider the x-axis only and take forces about the x-axis, because tension is in the x-axis or is along the x-axis. Right, in this case, we'd only be working with the frictional force and the tension, just 2 parameters. And we already know the frictional force Fk, right? So we can therefore be certain that we have to use the free body diagram from the 2 kilogram block. The reason we can't use the 8 kilogram block is here we would have to do a lot more work, and this is just 4 marks. First, we'll have to resolve this guy, the 62 newtons, so that we use its x component to then now find the tension, which is along the x-axis. Okay, and still we do not know what the frictional force is for the 8 kg block. So you see, that would be a bit tedious. It would take us a longer time. So that's why we use the 2 kilogram block to find the tension in this question. So let's do it. So we'll say F net. First, I choose right as my positive. Why did I choose right? Because the system is already moving to the right. Why would I choose left when the system is moving to the right? You can choose left. I'm not saying you shouldn't. It's just, it's convenient to choose right, okay? So that's something you always keep in mind whenever you choose directions. There's no rule to it, but do something that makes your life a little bit easier. Now we have F net is equals to MA. Now we have T going to the right, so therefore it's positive, plus my Fk, which is negative, because it's going to the opposite direction we consider as positive. So then we have our mass. Acceleration is going to the right, so it's positive as well. So now we can substitute our values. T, we were told that the frictional force is 2.1 newtons and our mass is 2. Our acceleration was given as 3 meters per second. Then from here we know that T is 6 plus 2.1, that should be 8.1 Newton. So that's our tension. This is our answer. Okay, so you see, it was less tedious. Imagine if we had used the free body diagram for the 8 kilogram block, we would still be trying to figure out FK for the 8 kilogram block, which is just not worth it for 4 marks. Okay, so here you are done. You're done with your 4 marks. Now we go to 4.3.2. Okay, let's do this. So here, before we go to 4.3 points, in case you're wondering why, if you check my free body diagram, you see that my vector for tension is longer than my vector for the kinetic friction. And then these two seem to be of equal length. Then the normal force and the weight. So since this block is moving to the right, it means whatever force is going to the right is way greater, or is somewhat greater than whatever force is trying to oppose the block's motion to the right. So that's why even on the free body diagram, the tension is bigger or is longer than the vector representing the kinetic friction. So that's how we usually think of drawing free body diagrams in general. So if you can, because in some situations, like in this case, I didn't know which one was bigger, whether it's tension or the friction, but I assumed it has to be the tension that's bigger. Okay, so, but in cases where you can distinguish it, make sure you do. It shows that you understand what you're doing. So now, let's go to 4.3.2. We say 4.3. Okay, so what do they want here? They want the coefficient of the kinetic friction. Let me copy this whole thing so that we have it here as well. So we are asked to find the coefficient of this kinetic friction between the 8 kilogram block and the 2 kilogram block. Okay, so we already know the friction, the kinetic friction for the 2 kilogram block. So now we don't know the kinetic friction for the 8 kilogram block, but they are asking us to find the coefficient of that kinetic friction. Okay, so where do we start? We start by solving for the normal force, right? Remember, the kinetic friction and the static friction are dependent on the normal force. So we try to find what is the normal force. And remember, for us to find the normal force, we take the sum of forces in the vertical direction. So I always prefer using that explanation rather than, there are people who have memorized certain equations, but they don't really know where they come from. So whenever you solve for the normal force, it's just taking the sum of all forces along the y-axis and then equating all of that to 0. The reason we equate it to 0 is because our motion currently is along the x. There's no motion along the y, so therefore it is 0. So let me show you what I mean. So you basically say sum of forces, or F net. This is for your own understanding. You don't have to say F net, but even if you do, no one will mark you wrong. So you can say F net is equals to MA, right? And then you take upwards as positive, okay? And if you remember our free body diagram for the 8 kilogram block, N is up, weight is down. But remember, we had components for this force, so we have to include them here, right? The reason for this is we cannot add the 62 Newton vector as it is when we try to sum forces along the x or y. So we usually use its components instead. So since we are working with the y-axis, we will use the y component of this 62 Newton vector. So how does it look like? you will have something like this. This is the 62 Newton vector, and then it will have, we usually treat it as a triangle, right? This will be its fx, which is the x component, and then this will be its fy, which is the y component. And this is just the 62 newtons, which is this guy going up there, right? So something like this. So now what happens is, and then we are given the angle, which is what, 25 degrees. Then from here we just use trig ratios. We know that if we take sine of 25, we will have fy, which is opposites over hypotenuse, which is 62. So we know that fy is simply, because we cross multiply, 62 sine 25 degrees. Okay, so this is what we're looking for, because we have to add this 62 sine 25 degrees. So let's go back. So now let us sum all our forces. We have N, which is the normal force, which is what we're trying to find here. Because remember, before we can find kinetic friction, we must know the normal force. Right, sometimes you don't have to know the normal force, you just need to know whatever vertical force is there. But in this case, we need to know the normal force. Right, plus weight, which is going down, plus, is the vertical component of 62 going up or down? Let's go check. We did it here. It's going up, okay? And then, therefore, it'll be 62 sine 25. 62 sine degrees is equals to, my mass is 8. Okay, I should have just substituted, but it's fine. Let's say MA. And then now we can start substituting. So N minus mg, which is 8 times 9.8 plus 62 sine, we should have started here actually, is equals to 8 times 3. Okay. No, sorry, my bad. We are taking vertical, so this should be 0. Right, so vertical, this thing is not moving, so that's why we equate it to 0. So this is why whenever you see those equations where people say N is Fy plus mg, something like this is where it all comes from. Okay, you're just taking forces along the y, so you don't have to memorize this, but you have to know where it all comes from. And then now you can say N is then equals to, you punch your calculator, I get 52.20 newtons. So that's your answer. This looks weird, NN. Yeah, I think that's why some people prefer to use FN. It's fine though, still the same thing. So let me use a big N so it doesn't look strange. So it's 52.20 newtons. Okay, now we proceed. They asked us specifically for the coefficient of the kinetic friction. Okay, so what if we sum forces now along the vertical, the horizontal, the x-axis? Sorry, this is not good. Proper. So we say F net is equals to MA. We're still using the same free body diagram, but now we're taking the x-axis. So we know, let's go, where's our free body diagram? Yes, we have T, we have FK. So we took right as positive, that means T and FK will be negative. And now we will have to include the horizontal component of this force as well, which will be 62 cos Fx in this case is 62 cos 25 degrees. Remember, if one is sine, the other is cos. If the one is cos, the other is sine. That's how it works, right? So, and then yes, we have that. Then now we can come back here and we can just plug in So we'll have t, we already know t to be 8.1, or we should write it by expressions first. I don't know, let's start there though. Minus t minus fk plus our fx is equals to ma. Okay, fx is a horizontal component of the 62 Newton force. Then minus t, we said is 8. What is 8 point what? 8.1 minus fk, we don't know fk, plus fx is 62 cos 25 degrees. M is 8 times 3. Okay. Aha, now we can solve for fk. Are we good? So fk, my f looks funny, sorry, but you can see it's an f. I'm going to punch my calculator. So fk, or the kinetic friction, is 24.09 newtons. That's what I get. So now, if you check, what I have now is I have the normal force and I have the kinetic friction. But remember, we are looking for the coefficient of the kinetic friction. And I remember what we said. Kinetic friction is calculated using the normal force. So what is the formula? We say Fk, kinetic friction, is equals to the coefficient of kinetic friction times normal force. But we are looking for this guy, the coefficient. So we can divide by n both sides. N. Therefore, the coefficient of kinetic friction is simply the kinetic friction itself divided by the normal force. We said the kinetic friction, we found it to be 24.09 divided by the normal force, which is 52.20. What do we get? I get that my kinetic friction is 0.46. Remember, the coefficient of kinetic friction, or coefficient of whatever really, usually does not have units, right? So not of whatever, but coefficients tend to not have units, right? So now we have that, and then that's it. This is a pretty high coefficient of kinetic friction, but it makes sense because this thing doesn't even have wheels. So now that's what we will have. And then what else were we asked to solve for? We were asked to find, oh yes, now we are on 4.4. Great. So 4.4, we are asked the angle at which the force is applied is now decreased to 10 degrees. Okay, if it is decreased to 10 degrees, 4.4.1 then comes and asks, how will the answer in 4.3.2 change? So in simple, what they are asking is, if I decrease the force at which this 62 Newton is being applied, what will happen to the coefficient of the kinetic friction, right? How do you think about this? So the way to think about it is in terms of, is it directly proportional or is it inversely proportional to the kinetic friction, right? And then let's bring it here. So if you remember our coefficient of kinetic friction, you have Fk and N, right? So if I decrease that force, it will affect my N, right? So my N is inversely proportional to that coefficient of kinetic friction. But then I must understand, how will it affect my N? Will it decrease or will it increase my normal force? Or how will it affect my excuse me, Fk? But let's focus on normal force, right? So now let's take this We can do it practically. We don't have to do it in our heads. Let's just substitute 10 degrees here, because they're telling us this 25 is decreased to 10 degrees. And let's see what's our new value. Okay, assuming we put 10 degrees here, our new value becomes okay, our new value, I get that it will increase to 67.63. So what does this mean? So let's come back to our equation here. We said Fk, kinetic friction, is equals to coefficients of kinetic friction times normal force. So this means that the kinetic friction will increase as well, because if you check, forget this, okay, we were dividing here, Fk times N. So you see, these two the kinetic friction, sorry, is directly proportional to the normal force. So if I decrease the angle, the normal force will increase, and therefore the kinetic friction will increase, because normal force, kinetic friction is directly proportional to normal force. But now here we are talking about the coefficient of kinetic friction. The coefficient of kinetic friction does not change. It cannot be changed by these forces, right? Because it's a property of a surface. Let me call it that. It's a property of a material, right? So it comes with the material. The coefficient of kinetic friction that you would get from rubbing your hands together is not the same as the coefficient of kinetic friction that you would get from rubbing, let's say, your hand against a tire, or your hand against your carpet. It will be different, because the carpet and the tire have different material properties. So it's a property of a surface. It depends on the surface, right? Some surfaces are more rougher than others. Some surfaces are more smoother than others. So that's why it will never change. So I wanted to make that sharp contrast so that you understand what the difference is. If they had asked us about kinetic friction, then we would consider everything I just showed you. You want to substitute and check what happened. You only compare to the normal force, by the way. You don't compare to anything else. What happens to the normal force is I change the angle. Okay, it increases. It means my kinetic friction will also increase, because kinetic friction is directly proportional to my normal force, right? If it decreases, then it means my kinetic friction will also decrease, because my kinetic friction is directly proportional to the normal force. But the coefficient of static or kinetic friction is, the coefficient of kinetic friction is dependent on the surface, so it will remain the same. Okay, it will remain the same. So we say remains the same, 4.4.1. So far away, remains the same, right? And then 4.4.2, that's where they want our reason. I said because it's only dependent on the type of surface. Or yes, let's use the type of surface. We'll say the coefficient the coefficient of kinetic friction is only dependent on the type of surface. So that's what we will practically say. All right, this is true excuse me, for all surfaces. Okay, now thank you very much for watching this video. This brings us to the end of this particular video. Catch us on our another video, and then I hope you enjoy it. Okay, bye.